Put your hand flat on the nearest surface, a table, a desk, your own leg. Feel that. The pressure, the resistance, the unmistakable sensation of solid meeting solid. Every instinct you have insists that your skin is making direct contact with something real. According to physics, taken as literally and rigorously as the mathematics allows, that never happens. Not once, not ever, not for your entire life. Every handshake, every hug, every step you've ever taken on solid ground has involved a gap, an infinitesimally small but genuinely real gap that nothing about your experience has ever crossed. That claim has become one of the most repeated facts in popular science, showing up in documentaries, late-night trivia, and endless online debates. What almost never gets explained is why it's true, what's actually happening in that gap, and this is the part that turns a fun fact into real physics, why a growing number of physicists think the popular version of this claim is itself an oversimplification, hiding something even stranger underneath. Here's why this question is worth taking seriously, rather than treating it as a party trick. Understanding why matter resists passing through other matter means understanding one of the deepest, strangest rules in all of quantum mechanics. A rule that doesn't just explain your inability to fall through your chair, but also explains why atoms have structure at all, why the periodic table has the shape it does, and why dead stars, collapsed under their own gravity, don't simply crush themselves out of existence. The story starts, as so many stories about atoms do, with a piece of gold foil and an experiment nobody expected to succeed the way it did. In 1909, physicist Ernest Rutherford's research team fired a beam of positively charged particles at an extremely thin sheet of gold foil, expecting the particles to pass through with only minor deflection based on the leading atomic model of the time, which pictured an atom as something like a uniform, pudding-like distribution of charge. Instead, while most particles sailed through as expected, a small fraction bounced backward at extreme angles, some almost straight back the way they came. Rutherford famously said it was as astonishing as firing a 15-inch artillery shell at tissue paper and having it bounce back and hit you. The explanation, published in 1911, reshaped atomic physics permanently. Atoms aren't uniform at all. Nearly all of an atom's mass is concentrated in an incredibly tiny, dense, positively charged nucleus at its center, surrounded by a comparatively enormous volume occupied by much lighter, negatively charged electrons. If you scaled a single atom up to the size of a football stadium, the nucleus would be smaller than a marble sitting at the 50-yard line. Everything else, by the classical picture, was empty. This discovery is where the popular story usually begins, and where the simplest version of the explanation comes from. If atoms are almost entirely empty space, arranged around a tiny core, then when your hand touches a table, the atoms of your skin aren't actually colliding with the atoms of the table's surface. What's happening in this classical picture is that the negatively charged electron clouds surrounding the atoms in your fingertip approach the negatively charged electron clouds of the table, and since like charges repel each other according to the basic rules of electromagnetism discovered by Coulomb in the 18th century, those clouds push back against one another before the actual solid material, the nuclei themselves, ever get remotely close. What you're calling touch is really electromagnetic repulsion, felt as pressure, mediated entirely by fields, with a genuine physical gap remaining between the charged particles the whole time. That explanation is a good start, and it's the version almost every documentary stops at. But it's not actually the deepest or most accurate reason matter resists passing through matter, and the real answer, discovered by physicist Wolfgang Pauli in 1925, is stranger and considerably more important to the structure of the entire universe. Pauli's exclusion principle states that no two identical fermions, a category of particle that includes electrons, can simultaneously occupy the exact same quantum state. Not prefer not to. Cannot, under any circumstances, as an absolute rule of quantum mechanics rather than a mere force or preference. As the electron clouds of your fingertip and the electron clouds of the table's surface begin to approach and overlap, more and more electrons are being asked, in effect, to crowd into the same region of space. Pauli's principle forbids this unless those electrons occupy increasingly higher, more energetic quantum states to remain distinguishable from one another. Pushing your hand further into that table requires forcing electrons into higher and higher energy configurations, a process that costs an enormous amount of energy very quickly, producing a repulsive effect called degeneracy pressure, or Pauli repulsion, that is, at the distances and forces involved in ordinary contact, considerably stronger than simple electromagnetic charge repulsion alone. Electromagnetic repulsion plays a real supporting role, especially at longer range, but it's Pauli's principle, a purely quantum mechanical rule with no equivalent anywhere in classical physics, that ultimately does the heavy lifting in keeping solid matter from collapsing into itself. This isn't a small, obscure effect confined to fingertips and tables. In its most extreme form, the exact same principle is the only thing holding up a white dwarf star, the collapsed remnant left behind after a star like our Sun exhausts its nuclear fuel. Without any nuclear fusion left to generate outward pressure, a white dwarf is held up entirely by electron degeneracy pressure, the large-scale version of the same Pauli exclusion effect, resisting your hand right now, straining against the crushing pull of the star's own gravity across an object roughly the mass of the Sun compressed into a sphere the size of the Earth. The same rule that stops you from falling through your chair is, at cosmic scale, the only thing standing between certain dead stars and total gravitational collapse. So the popular claim has real physics behind it, considerably deeper physics than most explanations bother to mention. But here's where the story gets genuinely more complicated and more honest than the tidy, "you never touch anything" headline suggests. Ask a physicist whether it's accurate to say two objects never touch, and you'll often get pushback, not because the underlying physics is wrong, but because the question itself starts to lose clear meaning once you take quantum mechanics fully seriously. In quantum theory, particles aren't tiny billiard balls with sharp, definite edges. They're described by wave functions, spread out mathematical descriptions of probability that don't have a single, precise location at all. When two surfaces approach each other closely enough to interact, their electron wave functions don't just approach a boundary and stop. They genuinely overlap, blending into shared quantum states in a very real, mathematically precise sense. The same phenomenon responsible for chemical bonding itself. In a helium atom, for instance, its two electrons occupy the exact same spatial wave pattern, distinguished only by an internal quantum property called spin, a level of intimate overlap that has no equivalent in the everyday, classical idea of two separate objects politely avoiding contact. Whether you call that touching or not touching becomes at that point less a question physics can answer for you, and more a question of which definition of the word touch you've decided to use. The gap the popular claim describes is real, in the sense that the charged particles themselves and the atomic nuclei never make contact. But the fields and wave functions surrounding those particles are, at the exact moment you feel pressure, doing something far more intimate than simply bumping into an invisible wall and stopping. There's a second complication worth taking seriously, and it pushes back on an even older piece of popular science, the claim that atoms, and therefore you, are mostly empty space. This idea traces directly back to Rutherford's discovery of the tiny, dense nucleus surrounded by a comparatively vast volume of, supposedly, nothing. But a growing number of physicists have pointed out that this framing quietly smuggles in an outdated, classical picture of what an electron actually is. An electron isn't a tiny dot of matter orbiting through empty space the way a planet orbits the Sun, with vast gaps of true nothingness in between. Under ordinary conditions, an electron behaves as a spread-out quantum wave, its probability genuinely distributed throughout the entire volume, that classical descriptions call the electron cloud. That volume isn't empty in any meaningful physical sense. It's continuously filled with the electron's actual physical presence, described as a smeared-out probability density along with the electromagnetic field the electron generates throughout that entire space. From this perspective, saying an atom is 99.99999% empty space misunderstands what size even means for a wave-like quantum object. You aren't mostly empty space in this more careful reading. You're mostly a dense, overlapping structure of electron clouds and electromagnetic fields, held together by exactly the quantum rules discussed throughout this video and by the same field-filled vacuum discussed elsewhere on this channel, which itself is never truly empty either. None of this remains purely theoretical or confined to blackboard equations. In September 2012, researchers at IBM, working with molecules synthesized at research centers in Spain and France, used a technique called non-contact atomic force microscopy to directly image individual chemical bonds within a single molecule for the first time in history, distinguishing bond lengths differing by just 3/trillionths of a meter, roughly 1/100th the diameter of a single atom. The technique works by dragging an ultra-sharp tip, itself terminated with a single carbon monoxide molecule, across a surface and measuring the minuscule forces, including exactly the Pauli repulsion and van der Waals attraction discussed throughout this video, acting between the tip and the individual atoms below. Physicist Philip Moriarty and colleagues have extended this technique specifically to probe and measure the Pauli repulsion force directly, atom by atom, essentially photographing the precise force responsible for every sensation of solidity you have ever felt. What was once a purely theoretical rule from 1925 is now something laboratories can directly image and measure, one chemical bond at a time. So what does this actually mean, taken together, rather than reduced to a single, tidy headline? It means the popular claim isn't wrong, but it isn't the whole story either. You have never brought the atomic nuclei of your fingertip into direct contact with the atomic nuclei of anything you've ever touched, and the force responsible for stopping that from happening is real, measurable, and considerably deeper and stranger than simple electromagnetic repulsion alone, rooted in one of the most fundamental rules quantum mechanics has ever discovered. But at the exact same time, the electron clouds mediating that sensation aren't hovering at a polite distance either. They're overlapping, interacting, and in a very real quantum mechanical sense, merging continuously every single time you press your hand against anything at all. Whether that counts as touching says less about the physics, which is well understood and precisely measured, and more about which century-old classical intuition about contact you're still holding on to. Your entire sense of touch, one of the earliest senses to develop, one of the ones you trust most completely, has been built by evolution entirely around detecting electromagnetic repulsion and interpreting it as pressure, texture, and solidity. Every object you've ever felt as solid has, at the deepest level physics can currently probe, been an intimate negotiation between overlapping fields and quantum states, resisted by a rule so fundamental it also holds dead stars together against the crushing pull of their own gravity, and so precise that scientists can now photograph its effects one atom at a time. You've spent your entire life certain of one thing above almost everything else. That touch means contact. Physics suggests the truth was always a little more intimate and a little more distant than that word ever really allowed for. The deeper we look into the universe, the more it begins to look back at us.